Hi everyone. Today I want to start chapter 7, which covers conversion and comparison instruction. But before I start talking about conversion and comparison instruction, we need to learn about binary coded decimal system, which is a number system. And this number system is basically a binary number system, and it has a very easy conversion process between decimal and binary coded decimal. We need to learn this number system before learning about conversion and comparison instruction and why we need these instruction at all. Okay, what is a binary coded decimal system? A binary coded decimal system uses 4 binary bits to represent each decimal number from 0 to 9 separately. Let me show you this by an example. So let's assume that we have a decimal number. So our decimal number is equal to 11. This is a 2-digit decimal number. And based on the definition of binary coded decimal, which tells us that for binary coded decimal, we need 4 binary digit for each decimal digit. So based on this definition, for 2 decimal digit, we need to have 8 binary digit to describe the binary coded decimal. So if I want to describe 11 in binary coded decimal system, that's going to be 0, 0, 0, 1. These 4 binary digit or bit describe the first digit here, and then I need another 4 binary bit to describe the second one. So I need another 0, 0, 0, 1, and that's the equivalent binary coded decimal number for 11 in decimal number system. Now, remember that the binary coded decimal, even though it is described in binary form, so you only see zeros and ones, but it's completely different with a binary value. So if I want to describe 11 in binary system, what I have to do is that I have to use multiple divisions. So I have to divide 11 by 2, and that's going to be 5 here. So I'm going to have 10 and 1 here. Then another division by 2. I'm going to have 2 here, 4 here, 1 as remainder. And then divided by 2, I'm going to have 1 and 2 here and a remainder of 0. So my binary equivalent is 1, 0, 1, 1. So this is the binary equivalent for 11. What I have here is the binary coded decimal equivalent of 11, and this is my 11 in decimal number. So it is very important to understand the difference between binary and binary coded decimal. The binary coded decimal is very easy to be converted into decimal, or from decimal to binary coded decimal, because you focus on each digit separately and you describe each single digit by 4 binary bit, and the conversion from binary coded decimal to decimal is also similar. So what you have to do is that you have to focus on each, partition them into 4 bits, and then convert them back to decimal equivalent. However, the binary conversion to decimal is not that easy, especially if your number is a big number, because then you have to do a lot of multiple division to get the equivalent number. And here you can see another example that you can convert this decimal number into its binary coded equivalent number by focusing on each single decimal digit and finding its equivalent binary value, and then putting these 4 bits beside each other, and that's going to be your binary coded decimal number. Now let me show you another an example here. I want to ask you a question. I want to know if the number that I'm writing here is a correct or valid binary coded decimal number. So this is my number, 10110110. My question is that, can I consider this as a binary coded decimal number or not? The answer is that I have to partition them into groups of 4. So if I partition them, then I have this one and this one. So it means that this number is a correct binary coded decimal because I have 4 digits, 2 4-digit, and each one can represent 1. But you cannot describe your binary coded decimal by, for example, 0 1 0 1 1 0 0 0 0, something like this. So then you have 4 here, you have 4 here, and then you have 2. So that's not a valid binary coded decimal number. Now the question is, why we need to learn about binary coded decimal? I'm going to show you here why we need that. So the end user or the operator prefer to work with decimal number. So if the operator or user wants to enter a set point, he will prefer to use decimal values. So it will wants to enter a decimal number. And at the end, when he wants to receive a number or monitor a value, for example, a temperature, again, this operator prefers to see decimal values instead of binary or binary coded decimal or any other number system. The preference of the user or the operator, either when he wants to enter a set point or a value into system, or when he wants to receive and monitor the output, is decimal number. But we know that PLC itself, PLC processor, works based on binary number. So the processor cannot work with decimal number, and it needs binary coded decimal. Now let's see what we can do here. What we have different type of input and output field devices that helps us to convert this decimal number into another number system. And that number system is binary coded decimal. So we have some devices that can convert the decimal into binary coded decimal, and we call them BCD push switches. So they are push switches that I'm going to show you in next slide. And these push switches will convert the decimal number into binary coded decimal. These are basically our input field devices. And then on the other side, we do have some output field device that they are capable of converting the binary coded decimal into decimal. So we have output field devices capable of converting binary coded decimal into decimal. What are these output field devices? You definitely know about them. The output field device that can convert a binary coded decimal into decimal number is 7-segment LEDs. So these are 7-segment LEDs. Okay, but remember that the problem has not been solved yet, because we are still having binary coded decimal, and the PLC processor understands binary number, not binary coded decimal. Same here. The output of the PLC processor will be binary value, not binary coded decimal value. So how we can make some arrangement here to make sure that we can convert the binary coded decimal into binary, and then binary to binary coded decimal at the end on the other side. The way that we can do this is using some instruction inside processor. So that's what we call conversion instruction. So using input and output field devices, we can convert our decimal into binary coded decimal, or the binary coded decimal into decimal. But in order to convert the binary coded decimal to binary for processor to work with the number, and then make sure that this binary output can be converted back to binary coded decimal, so then the 7-segment LED can display the number in decimal form for us, we need to use conversion instruction. This conversion instruction basically happens within PLC. So those are instructions in your PLC program. So the execution of program will be in form of binary, but all binary coded decimal can first be converted within the program into binary values, and at the end, when the program is completely executed, they can be converted into binary coded decimal, so we can feed them into our 7-segment LEDs. That's where we need to have conversion instruction. The conversion instruction that can convert binary coded decimal into binary, so what we have here basically, that can convert binary coded decimal into binary is FRD. That's an instruction which we call it as FRD, or from binary coded decimal. And then the other instruction that can convert the binary value to binary coded decimal is called TOD. So basically to binary coded decimal. So TOD is an instruction that we can use inside our program to convert any binary number into binary coded decimal, so we can prepare that to be fed into our 7-segment LEDs. And then in order to receive the input from push switches, which is in form of binary coded decimal, we need to use FRD instruction, which can convert the binary coded decimal into binary number. So in an FRD instruction, we do have a source and we do have a destination. Our source is going to be binary coded decimal, in binary coded decimal, and our destination is going to be in binary. So we have to either provide the value in binary coded decimal here for the source, or provide the address of this particular data, and at our destination we will receive its equivalent binary, so then we can use the binary that is provided by this instruction within our program. And then same thing we have for TOD. So TOD, just do the reverse conversion. So TOD instruction converts binary into binary coded decimal. So our source is binary number, or an address to a binary number, and our destination will have a binary coded decimal number, which is the equivalent value in BCD form of the original binary number.